Hi, my name is Noah Rauschkolb. I am a fifth-year PhD student in the Department of Mechanical Engineering at Columbia University, and this is my presentation for the NYSERDA Tenant Energy Data Challenge. We are primarily interested in the relationship between building occupancy and the load on each of these 18 meters. Throughout the month of March 2020, there's a very precipitous drop in building occupancy. That first red line shows when the first COVID cases appeared in New York, and the second is when the New York State went on pause and all non-essential workers were required to stay at home. Building occupancy stays very, very low until roughly the second week of June, which is when phase one reopening began. Slowly throughout June and then more steadily in July and August, people are returning to the building, but at a much lower occupancy level than what we saw before the crisis. If we turn our attention just to the load, here we have weekly load profiles for April through August in the years of 2018, 2019, and 2020. We can see that in 2018 and 2019, each of these 4 meters follows a pretty similar pattern. So during the weekends and overnight, there's some minimum level of consumption that's always happening on that meter. And then during the daytime, when people come in and start using stuff, load goes up. In 2020, what we see is that the peaks are way down, so that people aren't using as much power in the middle of the day because there are fewer people in the building. Remarkably, however, the minimums stay roughly the same. So in the nighttime, when there aren't a lot of people in the building, we're using about the same amount of energy just from keeping some computers on, keeping the copy machine on, that we were in previous years. When I wanted to get a better idea of what this relationship looked like between occupancy and load, the first thing I did was just plot data for each meter from right at the beginning of the COVID crisis all the way up through the end of August. So on the x-axis, we have entries to the building occupancy, and then on the y-axis, we have the load in kilowatts for each meter. What I noticed first, and I thought this was really interesting, is that right at the beginning of the crisis, we hadn't really adapted our power demand based on everything that was happening yet. And for quite a few of these meters, those really early points when building occupancy was really, really low, our energy demand hadn't really adjusted yet. Maybe what happened was people had left their computers running and they just stayed on until someone finally came in June and started shutting things off. So if you look at meter 13, for example, there's this big cluster of points right in the top left corner, and that completely skews the model of occupancy versus load. By removing those points, we actually get much cleaner fits for these linear models. And now for each meter, we have an idea of how much load increases as the number of occupants increase. Ultimately, I decided to fit an ordinary least squares model with fixed effects and interactions. This is a pretty plain vanilla model, and I think the only thing that's really special about it is the number of fitted coefficients. There are 4,320 coefficients. We got there because there are 18 units multiplied by 24 hours per day. We're looking at 5 different days per week, and we already saw that a Monday and a Thursday, the load doesn't look exactly the same, so we want to treat those hours differently. And then lastly, we have 2 coefficients for each hour, weekday, meter combination. There is an intercept term, and that intercept tells us how much we think the demand is going to be when there's nobody in the building, and then we've got a slope term. So the blue line shows all of the intercepts, and then the red line shows, well, let's assume a certain level of occupancy, add in those slopes, and we end up with a different shape for what we expect the load to be when people are coming into the building. Ultimately, the model has an adjusted R-squared value of just over 91%. Thank you for taking the time to watch this.